Okay, we're continuing to establish some of the properties of integers using just the axioms. And the next property we're going to establish is the fact that every integer has a unique additive inverse. So to show this first, we know that we already know that for every integer there is an additive inverse. That was the axiom of the additive inverses. So the only thing to show in this exercise is to show that the inverse is unique. So what that means is, so if we have, if A is some number, some integer Z, and let's say B and C are inverses, additive inverses of A, um, we want to show that, well, we don't know, we want to show that A is equal, so B is equal to C. So that means it's the inverse is unique. So how do we show that? Well, what does it mean to be inverses? It means that if we take A plus B, that's an inverse, so that means that's equal to 0. And C plus A plus C is also equal to 0. So that's the property of being for B and C being inverses. So one of the things, right? So now if we, and in fact, we have that in particular, this means that A plus B is equal to A plus C, okay? But we just established the cancellation law here, right? So if A plus X equals to A plus Y, then X is equal to Y. So that means that we can write, so B is equal to C. So this is by the cancellation law, which we just established. Okay, and that's it. So that means that the inverses are unique. Okay, so let's do the next example. So the next property of the integers is what's called the zero multiplication law. So let me actually start a new page. So let me just copy here what we want to show. Well, it says that actually I'm going to copy that there, and so we need to show that if I take any integer n and multiply by that by 0, I'm going to get 0. Okay, so how would we start this? So we want to show that well, let's use the fact that 0 is the additive inverse, additive identity, so I can write 0 equals to 0 plus 0. Okay, so in fact, this is going to be part of your homework, so I will include some of the steps, explanation for some of the steps, but not all of them, okay? So that means what? So n times 0 is equal to n times 0 plus 0. So what is this property that I'm using? It's clear that from here I have this is equal to that, so I'm multiplying both sides by n, which is like a specific law from multiplication axioms that I'm using. And now I can use a distributive property to write that n times 0 plus 0 is equal to n0 plus n times 0. And well, on the other hand, since 0 is additive identity, I can add it to the right hand side, to the left hand side, to write it like this. And finally, using the cancellation law, I would have here that I can cancel these terms here and write that 0 is equal to n times 0, right? So this is using the cancellation law. And this one here is using the fact that 0 is identity, additive identity. Here I'm using the distributive property. And here I'm using, well, yeah, what am I using here? You should tell that. And here in the first line, I'm using the fact that 0 is additive identity again, right? Because what is additive identity? If it says that A is equal to A plus 0 for every A in particular, so if A is equal to 0, I get 0 is equal to 0 plus 0. So that's what I'm using on the first line. So that's the 0 multiplication law, which says that if you multiply any integer by 0, what you get is 0 back. Okay, so the next property, some of the properties that are proved in the next example are the properties of negative numbers. So this include the facts that if you take additive inverse of the additive inverse of A, so that's what the minus means, right? You get A again. If you multiply A by -1, you get negative A. So what's the meaning of this? The meaning is that -1 is the additive inverse of 1, and you're multiplying that by A. What you get is an additive inverse of A, and so on. So you get other familiar properties of the integers. So you can look up in the book and see how they're proved. We'll just go over some of them. So for instance, number 1. So how would you show this property here? Well, it actually follows just from the definition. Let's remember that what is negative A, right? So what is negative A? Well, negative A is the additive inverse of A. So what that means, if you read that sentence backwards, that says that A is the additive inverse of negative A. So A is the additive inverse of negative A. Okay, and what's the meaning of the additive inverse of something? That means you have to, we have that A is just negative of that thing, okay? So if this negative A was a B, then A would be the additive inverse of B if A was equal to negative of B. So this is negative, negative of B, okay? So this is saying that A is equal to negative of B. So this is just going through the definition. Okay, so what about the second property? If you multiply A by -1, you get negative A. Well, let's see how you can show this property here. So imagine I add A to both sides. So let's add A to the left-hand side here. If I add that, well, from the previous property, well, actually, by the property that 1 is the multiplicative identity, I can write by A, instead of A, I can write 1 times A, okay? So I get negative 1A plus 1 times A. And then I can use, what property am I using here? In the second inequality, going from here to here. That's the distributive property. I can factor A out, and in parentheses, I have -1 plus 1, right? And because -1 and 1 are additive inverses, what you get is a 0 times A. And by the previous example, we know that if you take any integer multiply by 0, you get 0. So that means that -1 times A plus A is equal to 0. Okay, and now is that what we wanted to show? Well, if we subtract A from both sides, let's see. If we subtract A from both sides, we get this. So, so that proves this property. So let me just finish that. So using adding to both sides -A, what we get is that -1 times A plus 0 is 0 plus -A. So that means -1, -1A is equal to -A, which is what we wanted to prove. Okay, so I will let you read through the proofs of the other properties for negative integers, and I'll go to the next example instead.